So in these types of problems, what we want to do is have a look at substitution, where instead of the u being equal to a function in terms of x and then use the new variable, what we want to do is have the x as the old variable in terms of the new variable. So in this case, we want to have, we're given the substitution of x is equal to 1/5 of u squared minus 1. Now, like problems you've done already, you can manipulate this function however you like. You can rearrange it, and we can do that. 5x equals u squared minus 1, because there's our 5x there. Or you can get the 1/5 u squared minus 1 to be u is equal to 1 square root of 1 plus 5x, because we add the 1, take the square root. So we can manipulate it around that way. Now it's easy to manipulate here, because dx is equal to the 1/5 times 2u du, and the 2 that multiplies there, so it gives us the 2/5 du, 2/5 of u du. So there's our substitution for dx, which we can put in, and the square root of 1 plus 5x, so 5x was u squared minus 1, so we can substitute that in as well. Now we notice that 2/5 are there, the 1 plus the 1 minus 1 cancels, so it gives us the square root of u squared, which cancels. The u on top, well, u will cancel with the u, leaves us the square, integrate 2/5. I've left out the integral sign in those ones, which just gives us 2/5 of u plus the constant, or 2/5 of the square root of 1 plus 5x plus the constant. So you can see how it gets manipulated around. So 3x here is equal to u squared plus 1, and we're going to use that as a substitution for this function. So 3 dx is equal to 2u du, or dx is equal to 2/3 of u du. And then we can manipulate it and put u squared is equal to 3x minus 1, or u is equal to the square root of 3x minus 1. So we can manipulate it that way. Even x is equal to 1/3 of u squared plus 1, whichever one makes it easier. Which we can do that substitution, because that's x. Square root of 3x minus 1, well, 3x minus 1 was equal to u squared, so the square root of u squared works out nicely, and then dx is 2/3 of u du. So that the square root cancels with the 2 and gives us u. We've got the u there, the 2/3 times the 1/3 gets put out the front as 2/9. Then that's u squared times u squared gives us u to the power of 4. U squared times 1 gives us u squared. We can integrate that very nicely, and we do our integration, do our substitution to get our answer back like that. So in this one, we got x is equal to u squared plus 1. Gives us square. Again, we've got all these manipulations. You can stop the video and have a look at the manipulations we've got. Differentiate, rewrite it in different forms, and then we get u squared or function in terms of u. But we do our substitution, can make sure we're cancelling nicely, and then once it's in a nice form, integrate it, substitute back in. So and that follows the same way every time, even with a cos substitution. So again, we're looking at cos substitution here. Dx is equal to the minus 2 sine 2 theta, or minus dx would be minus a half dx sine 2 theta to theta. Now we can manipulate this one and split it up to get the sine 2 theta to theta there, which is what we need to do the substitution. So, and then we can keep manipulating that down till we get to a form where we can get the cos to the power of 4, cos to the power of 6, and then we can substitute the x in, because x is cos 2 theta. Integrate and substitute back in. So it goes the same way every time. When we're going to do definite integrals, so we want to move on now to definite integrals. Our substitution is going to work exactly the same way. So we do our substitution, we're looking for to substitute dx, so we can get 2x dx, or x dx there, which we're able to substitute in. We're going to be able to substitute in 1 plus x squared, but the problem is going to be in our integration limits there. So what we've got to do is, because we're going to change our function into integrating with respect to u, we've got to change our limits from being in terms of x to being in terms of u. And that's just a simple substitution, because if u is equal to 1 plus x squared, x is equal to 0, sub it in, we get 1, sub 1 in, we get 2. So our limits of integration will change as well as the variable that we're integrating with respect to. So you can see the substitution there and the change of the limits of integration. So, and then again, integrate. Anything that changes here at this point is that we sub in our points for u. We don't put it back in x at any stage. Because we've changed our limits of integration in the terms of values of u, we have basically got rid of the idea that we need to change the variable back in terms of x, and we just calculate it. So you can see in the derivative here, v sine x, so dv would equal cos x dx. Because v sine x, when x is equal to 0, v is equal to 0. And when x is equal to pi on 2, we get sine of pi on 2, which is 1. So that's why our limits become from 0 to pi on 2 of e to the power of v, which because v is e to the power of sine x, and because cos x dx was dv. So integral of e to the power of v is e to the power of v. Between 0 and 1, e to the power of 1 minus e to the power of 0 gives us e minus 1. We got t is equal to w squared minus 1, so dt gives us the 2w dw, so we're able to substitute in dt there. We got t, so we're going to put the w squared minus 1 in there, and 1 plus t, which will give us 1 plus w squared minus 1. Again, we put our two limits of integration. T is equal to 0, w is 1. T is equal to 1, we get w is equal to 2, root 2. So our limits of integration change from 1 to root 2. We clean our function up. So w squared cancels with the w and 1 on w. And then we're able to get it to a form where we can integrate and then do our substitution to get down to our answer. So again, we see in the same one here, 2 to 3. The 2 and the 3 because u is equal to x minus 1. So we sub in our values of x and we get our new values of u and as 1 and 2 in there. And then we were able to do our substitutions because du is equal to dx. So that swaps over nicely. And we can put our value of x in as u plus 1. Square root of 1 minus x was u to the power of a half. Expand our brackets. Integrate. Substitute. And simplify. And then we can see the same thing again here. That, well, when we're looking at some of this, it's an odd function. Like, technically we don't need to do substitution or any integration to do this one. That's an odd function. Because it's an odd function over an even function. And going to the same limit. So we know it should be 0. But it works out as 0 in this case. Because if you have a look, when you put the values of minus 0.5 into 0.5 into our substitution, so u is equal to 1 minus x squared, we get both the limits being 0.75. So it really doesn't matter what it's going to integrate to. Because they're both the same limits of integration there, that's going to give us 0. Which it should. Because if we drew this up, we'd get an odd function. And same values on but one's positive, one negative of a odd function means they're going to cancel each other out. But that's, you can see why that happens because we end up with the same limits of integration when we do our substitution there. So that's the nature of that one. So that's what we do. The only change we have to have when we go to definite integrals is putting our values and doing our substitution a little bit extra with the limits of integration.